Okay, so this is going to be, how do you spell Rutherford?
R
R, good, that's a good start.
U T H E R then 4.
Rutherford's, what are we doing? Gold foil experiment. Okay. Now, we're going to keep this very brief. It's not terribly involved. That's not to say in 1911 it was extremely involved. There were all types of things that were occurring in the science community which hadn't been done before, like this experiment. And what he discovered was outstanding. So let's talk a little bit about it. Now, you've read about some of the other models that were used to describe the structure of the atom. This is quite unique, actually. What he discovered was this. He took some gold foil, okay, and beat it very thin. And then he took a source of alpha particles. An alpha particle is actually a helium atom without the electrons. It's a helium nucleus. Okay? It's a helium nucleus. That's what an alpha particle is. So you're right, it's actually looked at. It has a charge of +2. It has a mass number of 4. It has an atomic number of 2. And then he put a screen behind it to see if anything happened to the alpha particles. And he found, to his astonishment, that some of them were deflected. Most of them went straight through, but some of them were deflected. And some of them were deflected a great deal. And some of them nearly went right back at him. Now, he said something to the effect of that shooting an alpha particle at a piece of gold foil and having it bounce back was like having a 15-inch, I think it was a 15-inch big shell, 15-inch artillery shell. Can you imagine this? Okay, 15. It's not a gun. It's like an artillery shell. A 15-inch artillery shell being shot at a piece of tissue paper, and the shell bouncing back at the artillery piece. You're looking at me like I'm crazy, but that's what it was like in terms of the forces involved, in terms of the momentum and the forces involved. Let's talk a little bit about, and remember, this is a different type of mechanics. This is modern or Einstein mechanics. Right? Mechanics means motion and forces and things like that. You're used to this. Classical mechanics. Let's just talk about classical mechanics for just a minute. Let me put a few things on the board just to show you how outstanding this is. Okay? Let's take a car. What's a car? Like 2 tons? right? Ish, right? Right? 2 tons, like 2,000 kilograms would be 2 tons, 2,000 kilograms. Is that about right? Okay. So a car, 2,000 kilograms, right? Now, in terms of I am 100 kilograms. So that's pretty heavy. Yeah, it's like 200 of me. It's pretty heavy. Yes? Well, no, that's not quite right. Sorry. 20 of me. So 2,000 kilograms is a lot of. It's a lot, right? Yes? Okay. What would the weight of that be? How do you get weight? Like, I'm 200 pounds, 220 pounds. What would the weight be? You multiply it by 10. That's acceleration. Due to gravity, 9.8. We'll round to 10, just to make things easier. There's a point to this that you are responsible for. So don't look at me like you don't need to listen to this. This is important. Clear? You sure? Okay. So that's going to be, so I'm 1,000 newtons. Kilogram meters per second squared. That's called a Newton, after Sir Isaac Newton. So my weight is 1,000 newtons. What's the car's weight? Yeah, it would be 20,000 newtons. You all right with that?
Yeah.
Are we there? Easy? So you see where that came from. The weight, 20,000. You all right with that?
Yeah.
Okay, good. All right, now. All right. So I just wanted to give you some idea of relative weight. Everything is relative. 20,000 newtons, you have no idea what that means, right? Unless I tell you that I'm 1,000 newtons. So 20,000 is big. It's heavy. Okay. The Greek letter lowercase rho, okay, that equals mass times velocity, which is momentum. Is that all right? Okay? You all right with that? Okay. Let's say you're all right with that? Yes? So let's say we have a 2,000 mass, right? So 2,000 kilograms. And how fast? Let's see, we have to make a conversion because we need meters per second. Okay? I can erase this, right?
Yeah.
Okay. So let's say some crazy drivers, okay? 140 kilometers per hour on E10, right? Faster than that, 160. Some crazy drivers on E10, 160 kilometers per hour. Okay? All right. So 160 right? Yes? And then you want to get rid of hours and go to seconds. So what does that equal? What is 160 times 1,000 divided by 3,600? Somebody give me that.
So
160 times 1,000 divided by 3,600.
44.444.
What is it?
44.444.
So can we just say 44? Is that all right?
Yeah, it's okay.
44 meters per second? Is that okay?
Yeah.
Yes? Remember that? Okay. So 44 meters per second. So what is 2,000 times 44 meters per second?
$88,000.
What is it?
88,000.
88,000?
Yeah.
You all right with that? 88,000?
Yeah.
You okay? All right, now let's say, so our momentum is 88,000 units. You all right with that?
Yeah.
Linda, you all right with that? Okay, all right. So if you come to a stop, what's going to be your change in momentum?
0.
No, that's going to be your final momentum, but what's going to be your change in momentum? 88,000, right? Isn't it?
Yeah.
Okay? It's going to be 88,000. Yes? We'll say negative 88,000. Is that okay?
Yeah.
You all right with that? We'll save the negative for later, but I need that negative for later, okay? All right. So 88,000, that's your change, right? You all right with that? Okay. So the change is going to equal that, okay? You with me so far?
Yeah.
All right, now, this is where it gets interesting. As they say, when the plot's about to thicken, the plot's about to thicken, what does the change in momentum equal? Well, it equals something called the impulse. What does that mean? Impulse is force times change in time. Force times time. So the change in momentum right? You okay with that? Now, if you're going 140 kilometers per hour or 44 meters per second, same thing. Did we do that right? Right? We did that right, okay. You sure we did that right? 160 times 1,000 divided by 3,600. Can somebody give me a verification on that?
161.
160 times 1,000 divided by 3,600. Just want to do a verification. 44? Okay, all right. How long do you think it takes you to stop without killing yourself? How many seconds? 2 minutes? A minute? Tell me.
1 minute and a half.
10 seconds. Look, I don't want to, like, you know, have a stomach bulge. Okay, so let's say 90 seconds. That's what Zayed said. He said it very quickly. Oh, all right, well, all right. We're going to say 90 seconds, okay? And we'll come back to your 10 seconds in a minute, okay? All right. So 88,000 equals F times 90. So what's 88,000 divided by 90? What's 88,000 divided by 90?
977.7.
977.7. Now, for me, you don't understand? Is that what you said? I'm solving for F, right? 1G. What does that mean, 1G? What's 1G? It's your weight, 1G. I weigh 1G, right? If I hit the floor from jumping over the desk, I might hit it at 2G. In other words, I might feel twice as heavy as I am, right? Okay? So I only feel my weight, so that's not a big deal. So 90 seconds is pretty cool. I just feel my weight, right?
Yeah.
Because I'm 1,000. I'm 10,000. Oh, sorry, a lot less than my weight. This is newtons. Sorry. So I weigh I feel a tenth of my weight. So that's not 1G. That's what? That's a tenth of a G, right? Right?
Yeah.
Is that right?
I think so, yeah.
No, guys, come on, guys, get with it. This is what? This is almost 1,000. That's almost 1,000. What's my weight? What's my weight? 1,000 newtons, right? So that's almost 1G, right? Yes or no?
Yeah.
You're sure? Okay? You get it? All right. So if you stopped so you feel your weight, is that a lot? It's okay? Yes.
I don't think it's videoing that side of the weight.
Well, let's check. Good catch. It is not. Well done there, big guy. Well done. Let's just turn this like this. Let's turn the whole thing. So it's not, but let's see if we can. All right, so let's move it back a little bit. And we'll turn it like that. How's that? Okay? Did I erase something in here? I didn't erase anything, right?
You erased 1,000.
Oh, yeah, but it was 1,000. 1,000 newtons is 1G, right? For me. Okay, yes? Okay. Now let's do what he suggested. Let's change this to a 10. Can I erase this now?
Yeah.
We'll change this to 10 seconds. And so what's that going to be? What is it?
8,000.
8,800?
Yeah.
You want to stop in 10 seconds? I'm going to feel 9 times my weight. Okay? I'm going to feel horrible, aren't I? What happens if I hit that dashboard? What happens if I hit the window? What happens if I hit the steering wheel? I'm going to feel terrible, aren't I? Right? Yes or no?
Yeah.
All right, good. So 90 seconds sounds a bit right, doesn't it? Okay. So if you don't have 90 seconds to stop, if you have a car, you're tailgating a car, what are they going to call you if you get into an accident? They're going to call you a puddle. You're going to be a puddle of tissue, a puddle of water. You're just going to be a puddle of organic substances. Okay? Broken bones, blood, tissue, just a puddle. All right? So, all right. Now, what happens if you hit a brick wall? What happens if you hit a brick wall going at that speed? How fast do you think you're going to take to stop? I mean, a brick wall.
Is it like one?
One brick wall, man. The brick wall is like 100 feet thick.
Okay.
Yeah, baby, it's a brick wall. What's going to happen? You're going to stop instantaneously, aren't you? Like how many seconds? Like 0.001 seconds, maybe? Right? Is that... Let me ask you this. Is that okay? 0.001 seconds? In a thousandth of a second? Aren't you going to stop instantaneously?
Yeah.
Well, what's instantaneous? 0.001? Is that all right? 0.0001? What do you want to say?
0.001.
All right, 3 zeros or 2 zeros? 2 zeros? All right. So 0.001 seconds. All right, what is 8,800 divided by 0.001 seconds?
Eight. Right. Yeah, that's right.
Is that right?
Yeah.
88 million. 88 million. You'll vaporize. You'll vaporize. Yeah, we don't even, yeah. And what happens if you bounced? You're going to be twice that. In other words, remember, momentum is a vector. So in other words, the change in momentum equals the momentum initial plus the momentum final. The change in momentum. Can you see that up there? So it's going to be the final minus initial. It'll be the final minus the initial, correct?
Yeah.
What did we say the final momentum was before we changed? What was it? Wasn't it 88,000 minus 88,000? Right? We're looking at the change in momentum. I'm saying the initial momentum here was negative 88,000, right? Well, let's say it's positive. Shall we say it's positive? Right? Isn't it positive? I'm going this way. We're going this way. We have a momentum of 88,000. Yes? Yes? If you're bouncing and it's a elastic bounce, what's your momentum going that way? Negative 88,000. So what's that? What's 88 plus 88?
$176. And then 8 zeros.
So now we're bouncing. So now what is it? Now it's really it's seriously instantaneous. So what is 176,000 divided by 0.0001? I added a zero. It's going to be 176,000,000,000,000. Right? So that's just a little bit of an idea of classical mechanics. What do we use classical mechanics for? What do we use classical mechanics for? Large objects. It's called Newtonian or classical mechanics, as opposed to modern or Einsteinian mechanics. So, let me ask you a question. This is strictly on the side. Are you ready? But probably could be, ironically, the most important part of the lesson. Are you ready? Let me ask you a question. Are you ready? Let me put this back. So the question would be, I'm going to ask you two questions. What will therefore, given all of this, what will therefore reduce the forces in a car crash? Increasing what? Increasing what? What is it? No. Yeah, but let's say you're going that fast. What would increase? Kenny, I know you had this last year, and you're sitting there. Yeah, you've got to increase time, right? Stopping time, right? 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 Aren't you got to increase the stopping time?
Yeah.
What happens if you increase the stopping time from 0.0001 second to 90 seconds? Piece of cake, right? Right? Now, what things that are in the car, there's 4 things that are put into a car that help to increase the stopping time. Not brakes. Airbags, right? Because you hit that airbag and your stopping time is increased, isn't it? What else? Seat belts. What else? Padded dashboards. What else? What's the big one?
Brakes.
We said not brakes, but yes, brakes, of course. Anti-lock brakes, for instance. But what else? Something you don't think of, really. It's the major difference, well, not the major, but it's one of the major differences between cars when I was a kid and cars now. What is it? We said seatbelts, didn't we? I think we said seatbelts, yeah. Crumple zones. In other words, the car crumples like an accordion. When I was a kid, it didn't crumple. I mean, it did a little bit, but not much. You hit a tree and the tree got hurt. I mean, you were hurt too. I mean, you were like a giant red puddle inside the car, but I mean, the car really, the damages were certainly severe, but you know, car crashes today, they look severe, but I mean, they look severe because they have the crumple zones. They're supposed to look severe. It saves your life. When I was a kid, I was in 2nd grade. It was spring of 2nd grade. And we had, I guess it was like 1962-ish, 63, maybe, 64 at the most. We had a 1960 Chevy Impala. The thing was like a giant aircraft carrier. It was enormous. It was enormous. It was enormous. And my mother said to my father, I remember the day they had the discussion, because we never took a long trip before as a family. This was like new. We went to Troy, New York, which was 3 hours away, but you would think that we were Christopher Columbus and company, you know. Oh, we took weeks to get ready for it. It was amazing. 4 kids, 2 parents. It was incredible, really. And we all were very comfortable in the car. And my mother said to my father, now, Tom, my father's name was Tom, make sure you get seat belts installed in the car. They were not, and this Impala was a pretty good car. I mean, it was like, you know, top of the line car, you know. You couldn't afford an Impala if you went out and bought a first car, unless you were working in a really good job today. It's a series car, even today. They're very small today, the Impalas, compared to what they were. They had these giant, you know, fins on the back. I'll show you a picture later, but white. It was amazing. It was a big car. And they didn't, standard equipment were not seatbelts. They were not standard. Amazing, isn't it? Amazing. I didn't have an airbag until, gosh, 90 somewhere. I think I had a Camry, 1999 Camry. It was the first car I had with an airbag. And I was like in my mid-40s when I first got a car with an airbag. And we've known all about Newtonian mechanics for 200 years. We've known it, 300 years. We've known about it. But for whatever reason, we never seem to embrace it very much. Okay. So when you're talking about these alpha particles, which are very small, traveling at 10% of the speed of light, hitting this gold foil and bouncing back, you're talking about an impulse that is tremendously high. You're talking about gold foil that is obviously heavier than tissue paper. So if you want to change things, it makes a little bit more sense now that you know a little bit about just a very simple example that you can all identify with driving a car. That when he said it was like, I think the quote was something like, it was like shooting a 15-inch shell, artillery shell, at a piece of tissue paper and having the shell come back and hit you. It certainly would kill you, but so those were the types of mechanical changes that were occurring. So what conclusions did he draw from this experiment? What were some of the very basic conclusions he drew from this? Anybody? Yeah, the atoms are mostly empty space. Now look at this. Look at this book, right? This book, it's not light. It's certainly light relative to the size of the Earth, but it's not, okay? I'm hitting my head with electrons, not nuclei. That's what I'm hitting my head with. There's certainly nuclei there, right, in terms of the collision, but that's the electron. So it's amazing, isn't it, that those things that the atom, this is mostly, if you took all of the electrons out of this, you wouldn't even be able to see the nuclear material that's left over. What would the mass of the nuclear material be that's left over? What would the weight of the nuclear material, what would the mass of the nuclear material left over if I took all the electrons away? It would be approximately what? The mass of the book. Do you know what a black star is, more or less? You know what a black star is? A giant star with all of the electrons ripped away from it and only nuclear material. Do you have your books there? I don't know if you have something as neat as something like, look, see if you can find in there, do we have the internet yet? Did anybody try? Laura, you seem to be shaking your head like you're definitely positive about that. Somebody look up for me, do they know the...
Doesn't work.
What is it?
Oh, we do.
Density of a black hole or anything like that? Is it in your book at all? Black hole density?
Doesn't.
Was that really important to do that? You got up and walked across, you walked in front of me and spit your gum out. That's a little weird, don't you think? Was that unnecessary? A little obsessive. Yeah, you don't, yeah. It's not, yeah. You don't do that. So it's never too late to learn manners. It's not a problem. Is the internet still not working?
No,
all right. All right, so then we're done. The internet's not working. So nuclear material is extremely dense. So the second thing he came up with, obviously there's something in the center there to deflect the alpha particles. And in order for it to be deflected back in the way it was, it's got to be massive. It's massive. Massive. And it was massive. The gold atom is much bigger than the alpha particle. What's the size of the gold nucleus? The alpha particle has a total mass, nuclear mass of 4. What's the gold? 200. What is it? What's the mass of gold? You can go right over there and look at it. AU. Zayed, you see it? What is it? In the middle of the table. Approximately.
79.
No, 79 is the number, the atomic number. What is it? 197. I knew it was more than 170, yeah. 197, okay? So, it's pretty big compared to that of a helium nucleus, right? So he said that two of the big things, and there's more in the book, that it's mostly empty space, and there's that nucleus that's enormous. Dense, very dense. It's got to be dense. How does he know it's dense? How does he know the nucleus is dense? Well, the alpha particle bounces back, but most of it passes through. So the nucleus is still small, but it's massive, it's dense. Yes? When he hits that, man, it's like hitting a brick wall, doesn't it? Caused an elastic collision, basically. Are we done? This is, what is this called? Rutherford's gold foil experiment.
Yeah.
Hey, listen, have a great Eid. We still got another good solid 15 minutes. Right? All right.